Alright, so now let's consider the glial cells, the support staff for our nervous system. There are different glial cells within the central versus the peripheral nervous system. In the central nervous system, we find a distinct population of glial cells. We have something called an astrocyte. Astrocytes, if we go with the analogy of a neuron being a rock star, an astrocyte, well, that's the manager. Astrocytes do all kinds of functions. They help reabsorb neurotransmitters. They help modify the environment. They help for the neuron, optimize the environment, help the neuron acquire nutrients. Pretty much anything that a manager would do for a rock star. They clean up debris. They help with the growth of the neuron by releasing growth factors. And they also help regulate the environment around the neuron. Ependymal cells, these guys right here, are only found within the ventricles of the brain. So we'll talk about the ventricles. And these are fluid-filled chambers within the central nervous system, where we'll say within the brain and brainstem, where blood is converted to something called cerebrospinal fluid. Right? Usually abbreviated CSF. You may have heard of that. We'll talk about the function of this later. We'll talk about protection of the brain. They help facilitate the production and the movement of the cerebrospinal fluid in these ventricles. There are specialized epithelial cells that line the ventricles. And then the last player here is something called an oligodendrocyte. Oligodendrocyte, and look at the name. Oligo means a few. Dendro means arms or projections, and cyte means cell. So it's a cell with a few projections. And these things form what are called myelin sheaths. Around neurons. That's going to be a huge factor for us. And what we can see here is one cell, and it has multiple projections reaching out and wrapping around axons of several cells. So one oligodendrocyte can actually wrap around several cells. And speaking of astrocytes, so here is an actual astrocyte within the central nervous system, a series of them, and here is a tracing of an actual astrocyte. And so when we say the star-like shape, because that's what the name astro means, astrocyte, we have multiple projections. It's a little more than a star actually, but one astrocyte can actually form over 2 million connections with neurons and other cells in the central nervous system. So it is wired to everything. Quite often, if something goes wrong, who do you think is more likely to have a nervous breakdown, the rock star or the rock star's manager as they clean up the mess? Well, it's going to be the manager. So most tumors in the central nervous system are not going to be neurons growing out of control. Usually, it's astrocytes. Oligodendrocytes have a very similar function to Schwann cells in the peripheral nervous system. So once we describe those, then we can come back and kind of highlight what these oligodendrocytes do. Within the peripheral nervous system, we find two distinct glial cells, satellite cells and Schwann cells. Satellite cells have a similar function as the astrocytes within the central nervous system. They're mini managers, if you will, which do some of the similar functions like reabsorbing neurotransmitters, helping to maintain an optimal environment around the cell body of the peripheral neuron. Schwann cells, that's where we're going to focus for a minute, because Schwann cells also form a myelin sheath around the axon of a neuron, but here they wrap individually. One Schwann cell will wrap directly around one axon. In fact, multiple Schwann cells will wrap around the same axon in a series, leaving little gaps in between. And that's what we're going to describe next. So let's take a look at a typical axon of a neuron. So imagine this scenario first. I'm going to put this in context. Imagine taking 10 steps. I'm going to take 10 steps, but I'm going to do heel to toe. So if I take a step and put my foot right there, and then take another step right up against that foot, right there, right there, right there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I took 10 steps. It took me a set amount of time. Imagine someone's walking across the surface, across your room. Now imagine I do the exact same thing. I take a step, but there is, I don't know, there's a cat sitting in the way. So I have to take a bigger step over the cat. Now there is a backpack. Another step. Now my son left a towel on the floor, which does happen a lot. Take another step. Now I've done, I don't know, there's something else. And there's something else. And that's kind of how my house looks like right now. We're all home right now, so it's quite a mess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Although I drew these a little longer, I admit, but I'm just kind of going fast. But do you notice I have to take bigger steps every time. I have to step over something, over something, over something. So I traveled a much greater distance in the same amount of time. It took me the same amount of time to take each one of these steps, but I traveled a greater distance, correct? In the same amount of time. And so if we have action potentials conducted along the axon of a neuron, that's a pretty straight line. That was cool. I'm getting good at this. That's better than I can do on a real whiteboard. So if we have, Pimagem sucks, but oh well. So if we have something in the way blocking the action potential, and so we'll actually see Schwann cells wrap themselves around an axon, all the way around. Wrap themselves all the way around. It's very difficult to draw on this thing, by the way. All the way around. Alright, you guys get the point. It's actually kind of fun to do. And you have to watch. You can fast forward. One more. All the way. Because I'm getting better at this. Around. There you go. No, it's not. But oh well. Right? So you can see there's these cells wrapped all the way around. And if we look at each of these cells end on, if we look at the axon end on, right? If we kind of sectioned through here, we would see the axon of the cell, and wrapped around the axon, these Schwann cells. And the Schwann cells actually wrap themselves around like a jelly roll, multiple layers over. The cell wraps around, wraps around, wraps around, wraps around, and wraps around. And so each of these represents that, right? And so these cells contain a lipid called myelin. And so as the Schwann cell wraps around the axon of a neuron, it forms what's called a myelin sheath. I might as well spell this out here. We're talking about Schwann cells. Don't forget, Schwann cells are only present in the central nervous system. And we start this off with a capital S, named after somebody, right? That's what we're illustrating here, Schwann cells. All right? So individual Schwann cells will wrap themselves around an axon. They contain myelin, and myelin is a lipid and acts like insulation. And so as the action potential travels, remember I made a big deal of this has to diffuse in, not along the surface. So that as ions diffuse in, that's kind of the key event in an action potential, they cannot diffuse again here. They cannot trigger an action potential because this region is myelinated. It's covered in a sheath of myelin. And so ions have to diffuse until the next available region, generating an action potential, and then they have to diffuse again. And then generating an action potential, diffuse again. Generating action potential, diffuse again. And so what do we see? Just like we saw with our elongated footsteps here. This is a much faster mechanism of conduction because these action potentials in a myelinated neuron, so spell this out, So in a myelinated neuron, action potentials can only occur in regions where there's no myelination. We call that a node of Ranvier. Capital R once again. Spell it with an R. It's a French name, named after somebody. And so these gaps where the action potentials can occur are called nodes of Ranvier. All right? And this type of mechanism, where we have action potentials jumping from node to node of Ranvier, providing for much faster conduction, is referred to as saltatory conduction. That's what we've described here. Saltatory conduction, and that's what this lesson was really about. So Schwann cells provide for saltatory conduction in the, well, that looks pretty cool, in the peripheral nervous system. And oligodendrocytes do the exact same thing in the central nervous system, except the way they wrap around the individual axons is a little bit different. All right, so let's consider one more thing here. All right, so let's put all of this into perspective. Let's consider myelinated versus unmyelinated neurons. Remember, myelin is a lipid, right? Myelin is a lipid. And lipid has a whitish yellowish hue to it. So when we get into the central nervous system, we'll actually talk about white matter in the central nervous system versus gray matter. White matter, gray matter. Why does it matter? Well, here's the idea. Think about it. White matter, gray matter. Which of these do you think will contain myelinated neurons? White matter or gray matter? Remember, lipid gives it that whitish grayish or whitish yellowish hue. So white matter consists of myelinated neurons. And the converse of that, obviously, gray matter, these are unmyelinated. So why are these such a distinction? In fact, if we take a look over here, right, we can tell right off the bat. Gray matter, white matter. We have gray matter here and white matter here. Right, we can clearly see the distinction. So why do these neurons not need to be myelinated? Or in other words, why do these need to be myelinated? Remember what myelin does, right? What is saltatory conduction? Conduction is much faster in saltatory conduction. So therefore, white matter is conducting much faster than the gray matter. And if the white matter is conducting faster than the gray matter, where do you think we need that faster conduction? Or where would it be beneficial to be, well, not slower, but we don't need that speed, the velocity? Well, if we have a processor versus communication. So small cross-wired were referred to as interneurons within the central nervous system. These are the processors. They form all those functional regions, the basal ganglia and the different parts of the cortex with various functions and parts of the brainstem with their discrete functions. That's gray matter, unmyelinated processors. Whereas white matter is going to be the communication. And we'll talk about different types of tracks of white matter, connecting the various processors, or linking those gray matter interneurons together so they can work as one unit. Think of an apple pie, right? There's the taste of apple pie. There's the smell of apple pie. There's your grandmother's kitchen. All these thoughts come in together. The smell, the taste, the sight. Some mathematicians out there start thinking of, 3.14, the numerical value of pi and the circumference of the sphere and so on and so forth. I think of McDonald's apple pies, but that's just me. Good stuff right there. But all those are very different parts of the brain working together. How can all those various modalities, right, those little clusters of interneurons work together? it's the white matter tracks that link them together. So we'll see that's a key function. We'll see commissure, association, and projection fibers all working together to allow the brain to work as one cohesive unit, to allow the central nervous system to work as one cohesive unit. So in the central nervous system, there's a distinct difference between gray matter and white matter, both structurally and functionally. Here's one more for you guys. Check this out. All right, so here we can really see that distinction. This is a coronal section through the brain, kind of coming down right about here. We'll define all these regions later, but take a look what we see. Right off the bat, it's blatantly obvious. We have kind of this crust of gray matter in the periphery. We mentioned in cortex or neocortex, that's what we're talking about, that outer crust or cortex. We find deeper structures. This is the thalamus and the hypothalamus. We find gray matter within the brainstem here. That's the pons, and there's the medulla oblongata going down the spinal cord. These spaces are actually normal, right? And this right here, you guys see that right there, little cluster there? These are some of the basal ganglia. This is actually, this one here is the striatum, and that's the caudate nucleus. That's the one that's in my son's disorder. That's what the inflammation occurs because of encephalitis, that little cluster right there. And then here's more gray matter, right? So the idea is those are all processing. Whereas the white matter tracks, you can actually see it here. Look at this. This is the corpus callosum. It's called commissure fibers. We'll describe later. This bridges the two halves. It allows the two halves of your brain to work together. In fact, if that's severed, we actually see some really interesting characteristics. Some really interesting things occur when that's severed, the connection between the two hemispheres. They start working independently. And look at all the white matter tracks, cross-wiring, cross-linking all the gray matter, allowing it to work together. So it's not just the processors, but how the processors are connected by white matter. Right? Gray matter processing, white matter communication. Easiest way to think about it. Structure-function relationships.